Hi guys, what's up? Today I am going to show you how I built the upper encoder joints. They are used for the orientation of the wrist. In the bottom part we have the joint 4. In the middle joint 5. And the top one is the joint 6. I already glued the magnets on top. In order to see the movement of each axis, we are going to mark them to see how they react when we backdrive the wrist. Since the 3 joints are built in joint 3 frame, there is no direct link movement from each motor to its joint. Let's see this example starting backdriving joint 4. As you can see, all motors move in the same direction, which means joint 5 and joint 6 are dependent on joint 4. Let's see what happens when we move joint 5. Only motors 5 and 6 move, but in this case they turn in different directions. Joint 5 in this case is also dependent on joint 6. Let's move the last joint 6. In this case happens something similar to joint 5 with the difference that they turn in the same direction. We can take a conclusion from this: joint 5 and 6 are fully dependent from each other. Now we are going to proceed to assembly the encoder supports. First we need to unscrew and remove the 4 screws in the backside of the stepper motors. I will use this 3D printed plastic supports to attach the encoders to the backside. As joint 1, 2 and 3, these encoders are also built in 14-bit resolution, which means we can count a total of 16,384 values per evolution. Dividing 360 degrees by this value, it gives us a theoretical resolution of 0.02 degrees in the motor output, which is quite astonishing. On top of that, resolution is increased by the gear ratio of these stepper motors. Now let's put the screws back, and tighten the supports. Let's see now how this motors move in automatic mode. In this example, all these 3 motors are moving following a point-to-point synchronization. Note that lower joints are deactivated for this test. Finally, it only remains to put the covers on top. For this we need to press gently until you hear a light click.